Hello, my name is Jessica Solider, and today I'll be talking about inverse trigonometric functions. So, what are they? Inverse trig functions are often used to figure out an angle from its trigonometric ratios. They are the inverses of sine, cosine, tangent, secant, cosecant, and cotangent, but I will be just focusing on cosine, sine, and tangent. Another way to put this is by saying that inverse trig functions require that a number is plugged into a function and the output is an angle, more often than not expressed in radians. So basically our main goal is to find a given angle based upon... Okay. The first term on our list is theta, which is often used to represent an unknown angle. The unit circle, which will be a helpful tool, and I'll discuss later as I use it in our examples. It should be familiar to everybody though. The domains and ranges of functions as defined in the book become inverses of each other, and this will become more prevalent later. Inverse relations are written as such, and you'll see them as I start to work out some problems. This is the inverse of cosine, the inverse of cotangent, inverse of secant, sine, and tangent. The domains and ranges of functions as defined in the book become inverses of each other, and this will become more prevalent later. Inverse relations are written as such, and you'll see them as I start to work out some problems. This is the inverse of cosine, the inverse of cotangent, inverse of secant, sine, and tangent. I forgot to put cosecant on there, but you get the idea. So, before we begin, take a look at these relations and realize that they are equivalent. Pretty basic, but just a good idea to acknowledge it. So, for the first example, I would like it if we could attempt to write the inverse of the relation of x which equal of sine of theta. The answer is theta is the inverse of sine of x, or theta is the arcsine of x. Arcsine is the same as the inverse of sine, written with a -1 as the exponent, but I prefer to use this one, and I will in these examples because it's what's in our calculator and it just makes more sense to me. So how does this work? X is of the cosine of theta asks for the angle that is plugged in right here to get x. We isolate the angle theta by rewriting the given equation as the equivalent theta equals the inverse sine of x equation. Okay, example 2. Here we're going to take the inverse of sine of 1/2. We know that the sine of theta is opposite over hypotenuse. Theta meaning, again, any angle, and that's pretty standard. But here we're doing the inverse, so what we need to do is take the inverse of sine and plug in opposite over hypotenuse, and setting that equal to theta, so we are switching the terms, hence inverse functions. So if we see this on a triangle, on a right triangle, we can see that we have side 1, with a length of 1 and 2, and angle theta located at the lower left, and theta is equivalent to sine, the inverse sine of 1/2, and this is what it just basically looks like on a triangle. Okay, continuing on with the example, we need to find the missing side before we can do anything. So we have 1 squared, the missing side will represent b, and we set that all equal to 2 squared. It's the Pythagorean theorem, so 1, we're going to eventually end up with 1 plus b squared equals 4, and we need to subtract the 1 from both sides, and that is b squared equals 3, and I took the square root of each of them, so b is going to equal the square root of 3. So what we do with this is we take a look and we realize that the square root of 3 is larger than side 1, and we already know that side 2 correlates to the 90-degree angle. So because square root of 3 is larger than 1, we need to make sure that the angle across from it is 60, and the angle across from this side length of 1 is 30. What we do now is we need to convert these degrees, 30 and 60, to radians. On the unit circle, this is where that comes in. So because the angle theta is 30 degrees, it's equivalent to pi over 6. And because angle 60, just for extra practice, because this won't actually come in handy, but the angle 60 is equal to pi over 3. So what we do with this, how we get our answer, is we know that theta, which is right here, is equal to the inverse sine of 1/2, which equals 30 degrees, which equals pi over 6, as we just described in all these steps. So our answer is pi over 6. For our third example, we're going to evaluate the tan of the inverse sine of 5 over 13, 5/13. I mean, we're going to assume that all angles are in quadrant 1 just to make everything a little bit easier. So, to begin, we're going to take the sine of the inverse sine 5 over 13. And by substitution, this will make it 5 over 13, and it'll just make it a little bit more simple for us. And this is how we know that it's in quadrant 1, because 5 over 13 is greater than 0. So to be in quadrant 1 or quadrant 2, we're going to focus on quadrant 1. So what we can do in respect to that is create an angle and find a workable triangle. So we have our side length of 5, and side length of 13, knowing that sine is a relation of the sides on a triangle. And we're going to put x for the missing angle, and we're going to let a, for this example, represent the inverse sine of 5 over 13, just to make it a little bit prettier. So to continue, we need to find it's important to know that a tangent ratio is sine of some number over cosine of some number. So we're going to continue to use a to substitute the inverse sine of 5 over 13. So we must write that tan a is equal to sine a over cosine a. And we know that sine a is 5 over 13. So we have to find cosine a to figure out tangent a of a. Okay. So here is our reference triangle again. So what we need to do is we need to find the missing side before we can do anything. So we know that x squared plus 5 squared equals 13 squared based upon the Pythagorean theorem. I showed a little of the work, but we know that it's a 5, 13, 12 triangle, or we should. So cosine of a is 12 over 13 because cosine is opposite over hypotenuse, and on our reference triangle we can see where we can get this, where we get the relation. Okay, so to solve, we have to take tangent. We're taking tangent of a, or the inverse sine of 5 over 13. So if you can see, I kind of converted the tangent of a, our basic sample problem to help us solve, and made it 5 over 13 divided by 12 over 13. So to figure this out, we just need to do some simple math. When you divide fractions, you have to flip one of the fractions and simplify. So I'm taking 5 over 13 times 13 over 12 after I flipped it over. And you can cancel out both of these 13s, making them both 1. And so that's basically 5 over 1 times 1 over 12, equaling 5, or coming to the answer of 5/12. So for our final example, we are going to use an equation. So we're going to take the inverse of cosine of x, set it equal to the inverse of sine of negative 5 over 13, and we're going to solve for x, obviously. So what we're going to do is similar to another example I just gave, and we're going to take the cosine of the inverse cosine of x, that will substitute it, and that'll kind of, because these are inverses of each other, they'll cancel out, and it'll equal x. And this will be, so what we do on one side, we have to do the other, obviously, basic rule of math, so we're going to take the cosine of the inverse of sine of negative 5 over 13. So we're going to have x equals the cosine the inverse sine of negative 5 over 13. So continuing on, we're going to have, like I said, x equals the cosine of the inverse sine of negative 5 over 13, if I can't say that enough. So what we're going to say is that the inverse sine of negative 5 over 13 is equivalent, remember those relationships I showed you? It's equivalent to the sine of theta is equal to negative 5 over 13. So you can rewrite it and write it as this. So I'm going to put this on a graph again, and this is our reference triangle. We have 13, 5, angle theta, and an unknown side. I'm pretty sure we can all assume that it's going to be 12, because it's a 5, 13 triangle, right triangle. Alright, so inverse functions. This is going to be some angle, so we're just going to call this whole thing theta. In the last little paper I showed you another way to rewrite that, but that we can disregard for now. So x is equal to, it will become x is equal to the cosine of this angle that the inverse sine of negative 5/13 makes. So we're going to put this on the triangle. Theta, here's side 13, here's side 5, just to be familiar, and this is my work showing how this missing side is 12. And we're going to move on. So to figure out, we need to figure out what exactly the cosine of theta is. So we know that cosine is adjacent over hypotenuse, the sides. So we're going to take 12 over 13. And this is going to be our answer. X is going to equal 12 over 13.